sorry.
Okay.
Yeah.
I would kindly like to ask you to please go to full screen.
Yeah, I will do it. Hold on.
To please cut very short your talk, because we lost more than 10 minutes in the beginning. Obviously, I think the introduction about QCD is probably not necessary.
Yeah. I'm very sorry for the delay.
Please only present the specifics of your calculations, because it's what people would be most interested in, simply to save time, because we are already quite late.
Okay.
Then it's my pleasure to introduce Halil Mutuk. He will talk about the cascade CC, baryon, and from a quark-diquark model perspective. Please go ahead.
Okay, thank you very much. I will do my best in order to gain the time very short. This is the outline and the introduction part. As Christoph said, I can skip all of these stuffs. And also we know that the mesons are bound states of quark antiquarks and baryons are bound states of 3 quarks. So what is diquark? It's a color-bound state of 2 quarks, and although it has not been observed yet. In terms of color structure, 2 quarks can behave like an antiquark, and 2 antiquarks can behave like a quark. So we all know that the baryon is composed of 3 quarks, and it is natural to handle the baryon as a 3-body problem. But the possibility of pairwise clustering of quarks inside the baryons have been studied in the early days of the quark model. And in addition to this, there are some indications for the diquark-quark model in baryon, such as mean separation, anti-symmetrizing the wave function, and the reducing of degrees of the freedom for the calculational purposes. So the cascade baryon was observed in 2017, and it has triggered many phenomenological studies in the literature. Since this is a doubly charmed quark, it is believed that the charm diquark, if it is, may play a role in the dynamics. So what we have did, we have think that the cascade CC baryon composed of a CC diquark and an up quark, and we used a phenomenological potential model with the Cornell potential plus spin-dependent terms. We basically solved the regarding Schrödinger equation. We have taken into account all possible diquark clusterings, such as you can see that if you see a diquark in a symmetric state or the anti-symmetric state, and we calculated the mass of the cascade CC baryon. Results can be seen as follows. And we also calculate the wave function at the origin, which is an important quantity, since a large value of the wave function at the origin corresponds to a compact state. And we found that if a CC diquark in the cascade baryon has a lower value of the corresponding wave function at the origin, but the other possibilities in the diquark clustering has a larger value of the wave function at the origin. This is the table that we have compared with our results in the studies from the literature. We also calculated the magnetic moments for this state. And we have found a very small value, which I believe it is not accessible for in the future experiments, because these values are rather small. And the magnetic moments of the excited states, we also calculated these and compared with the literature. For further details, you can see the following paper, which was published in the European Physical Journal Plus. And to gain time, the discovery of the double-shaped barium may provide for the possible triply heavy baryon states, but the most important thing, as I believe, is that it may open an understanding of the exotic hadrons, such as the BBU bar D bar tetraquark. I mean, this paper, I believe, that is important and is a consequence of this observation. And thank you for your attention, and I apologize for the delay. Something was happened. I'm sorry for that, and I hope that I'm not very fast for the presentation.
Well, I'm impressed. Actually, you made up a lot of time. We are more than back to schedule. Sorry, I didn't want to rush you that much, but that gives us some more time for questions. Are there questions for the audience? Comments, remarks?
By the way, this is our campus from the bird's eye view in Samsun, Turkey. Just to mention that.
Okay, if there are no comments from the audience yet, then I have a question. Can you go to page 13?
Yes.
You said you take into account all possible diquark clusterings. Does that mean also all possible diquark clustering with respect to color? Do you have the 3 bar and the 6, or only the 3 bar, as many do?
The second one, as you said, we just think about the color structure.
So we just have the color 3 bar, not the 6.
Yeah, 3 bar. Yeah, not yet.
And something that you might have mentioned, but I missed it, is how do you actually treat your diquark? Do you treat it as a point particle or as an extended particle?
Yeah, I assumed that it was a point-like particle, but in the literature, diquark, I mean, has a sizable range, but we didn't take into account the size of the diquark. We assumed that it's a point-like particle.
Okay, and do you envision to include a diquark size in future calculations?
Yeah, it's my future work. I'm planning that.
Okay.
It's important, I mean, the size of the diquark.
Well, it also gives us some hint probably on the accuracy of your calculation, right?
Yeah.
It would be good to get some feeling for how important that is to judge on the reliability of the numbers.
Yeah, you're right.
And still no hands raised. So for one last question, can you go back to the table of the magnetic moments?
Yes, this one is the ground state.
Yes, and here I see that the magnetic moments scatter by almost 2 orders of magnitude.
Yeah.
For instance, when I look at the QCD sum rule value compared to your number, it's not a factor of 100, but a factor of 50, which is already pretty impressively large. Do you have an idea what the origin of these huge differences are?
Yeah, I actually argued in the paper your question, but as you can see that there are really, the results are so much scattered from different to different models. And
but you're by far the smallest, right?
Yeah, I am you are right. I am the smallest one. Maybe just value for the chiral constituted quark model. It is lower than me, but my results are lower compared to the literature.
Okay, good. Well, if there are no further questions or comments, I think we now have a break of some 15 minutes. Well, actually, we can even take a little more. We